This is the Nerd-A-Pult. Today we are going to use it to do an introductory projectile motion problem.
Ow! What was that?
Flippin' physics.
I purchased the Nerd-A-Pult from Carl and Mary Hauser of Ancient Artillery, and you can get your own at marshmallowcatapults.com. And as you can see from the title of the website, it is originally intended to launch marshmallows.
Yeah.
However, because marshmallows are heavily affected by the force of drag, I retrofitted mine using this bottle cap to hold this ball instead. Let's get to the problem. Billy, could you please read the problem?
Sure. A ball is launched from the Nerd-A-Pult with an initial speed of 3.25 meters per second and an angle of 61.7 degrees above the horizontal. If the basket is 93 centimeters from the ball horizontally, where should the basket be placed vertically relative to the ball so the ball lands in the basket? So let me get this straight, Mr. P. We know the displacement in the x direction of the ball will be 93 centimeters, and we are trying to find the displacement of the ball in the y direction, right?
Yes, Billy, you are correct. Basically, we know the horizontal displacement from the ball to the basket is 93 centimeters. We know the initial velocity of the ball, and we're trying to figure out where to place the basket vertically relative to the ball such that the ball will land directly in the basket. And yes, I did get this from my children. And in case you're curious, I did make a video of how I determined the initial velocity off the Nerd-A-Pult, and you are more than welcome to watch that. Bo, at this time, could you please begin solving the problem?
Well, the ball is an object in projectile motion, so we need to list our givens in the x and y directions. We know the acceleration in the y direction is negative 9.81 meters per second squared. We also know the displacement in the y direction is what we're trying to find, so delta y equals question mark.
And the displacement in the x direction is 93 centimeters.
Yeah.
And we need to convert that to meters, so multiply by 1 meter over 100 centimeters to get 0.93 meters.
Good. What else? What about this initial velocity?
The initial velocity in the x direction is 3.25 meters per second.
Actually, I think 3.25 meters per second is the initial velocity in the y direction.
No, the initial velocity in the y direction is 0.
Actually, I'm sorry, but none of those statements are correct.
Components. We need to break the initial velocity into its components. Velocity initial in the x direction, velocity initial in the y direction.
Yeah.
Bobby, you are correct. The initial velocity needs to be broken into its components. The initial velocity in the y direction and the initial velocity in the x direction. And Billy, could you please find either component of the initial velocity?
We know sine theta equals opposite over hypotenuse, and opposite theta initial is the velocity initial in the y direction, and the hypotenuse is the initial velocity. Multiply the whole equation by the initial velocity, and you get the initial velocity in the y direction equals the velocity initial times the sine of the initial angle. We have all those numbers, so it is 3.25 times the sine of 61.7 degrees. Which is 2.86155 meters per second.
Now that we know our initial velocity in the y direction, I have added that to our y direction known values. And Bobby, could you please now find the initial velocity in the x direction?
We know cosine theta equals the adjacent over the hypotenuse, and adjacent to the initial angle is the initial velocity in the x direction, and the hypotenuse is the initial velocity. Multiply by the initial velocity, and we get the initial velocity in the x direction equals the initial velocity times the cosine of the initial angle, or 3.25 times the cosine of 61.7, which is 1.54079 meters per second.
Now that we have figured out the initial velocity in the x direction, I have added it to our x direction known values, and we can really begin solving the problem. So, who can tell me which direction we can start with, how we know we can start with that direction, and what exactly we are solving for? Yeah, Bo?
We know two variables in both directions, and we actually need 3 to solve in the y direction, but we only need 2 to solve it in the x direction. So we should start with the x direction. And we're solving for change in time because delta t is a scalar.
Very good, Bo. Bobby, could you please begin working on the x direction?
We know the velocity in the x direction is constant, so it's not just the velocity initial in the x direction, but rather it's the velocity in the x direction for the whole time. And we know the velocity in the x direction equals the change in position over the change in time. We can multiply both sides by the change in time to cancel out change in time on the right-hand side. And we get the velocity in the x direction times the change in time equals the x displacement. Now we can divide the whole thing by the velocity in the x direction, and we get the change in time equals the x displacement over the velocity in the x direction. Substituting in numbers gives us 0.93 divided by 1.54079, which is
0.603588 seconds.
Now that we have the change in time, which is a scalar, which means that it's independent of direction, we can add that to our y direction knowns and solve for the displacement in the y direction. Bo?
Because the acceleration in the y direction is constant, we can use the uniformly accelerated motion equations. So the y displacement equals the initial velocity in the y direction times the change in time plus 1/2 times the acceleration in the y direction times the change in time squared. Plugging in numbers gives us 2.86155 times 0.603588 plus 1/2 times negative 9.81 times 0.603588 squared, which works out to be negative 0.059785 meters.
Great, I'm going to multiply our answer by 100 centimeters over 1 meter to convert to centimeters and round to 2 sig figs. And we get negative 6.0 centimeters for the displacement of the ball in the y direction after being launched by the Nerd-A-Pult and traveling 93 centimeters in the x direction. In other words, if the basket is 93 centimeters away horizontally, it needs to be placed 6.0 centimeters vertically below where the ball is initially launched from. And it turns out the basket is already 6.0 centimeters below where the ball is already launched from. You know what, actually, let's go outside where there is more light, which allows a faster shutter speed so the ball won't be just a blur, and we can show it in slow motion.
Yeah. Woohoo! Oh, it went in, but it got rejected. It bounced back out.
Wow, that actually worked.
I like it.
Good job. Thank you very much. Let's do a quick review. We drew a picture. We listed everything we knew in the x and y directions. We broke the initial velocity into its components in the x and y directions. We were then able to use the equation for constant velocity in the x direction to solve for the change in time. The change in time is a scalar, so we were also able to use that in the y direction, and therefore we could use a uniformly accelerated motion equation in the y direction to solve for the displacement in the y direction. Thank you very much for learning with me today. I enjoyed learning with you.